Climate datasets are crucial for understanding past, present, and future conditions for species. They provide valuable insights into long-term trends from the past, as well as projections of what we might be able to expect in the future. These long-term datasets and projections support research and enable scientists to assess climate risk in order to inform policy and decision-making. Future climate projections are a particularly valuable tool because they allow us to forecast how the climate might change in the coming years based on human behaviors and what those changes will mean for the planet. Future climate projections are created by simulating the Earth's climate system using complex computer models that incorporate factors like atmospheric conditions, ocean currents, and land surface processes. Scientists can then input different scenarios of greenhouse gas emissions to observe how the climate might change if certain behaviors or policies are adopted. The Intergovernmental Panel on Climate Change, or IPCC, is an international body established by the United Nations to assess climate change science and impacts. The IPCC uses two sets of scenarios to analyze future climate change impacts and potential responses. These two scenarios are known as the Shared Socioeconomic Pathways, or SSPs, and the Representative Concentration Pathways, or RCPs. These two sets of scenarios capture different aspects of climate change and are used together to explore different potential futures. The SSPs include 5 narratives that aim to describe plausible future socioeconomic developments. The 5 scenarios map a range of challenges to increasing climate change mitigation and challenges to increasing adaptation. At one end is a sustainability scenario where policies are focused on sustainable development. There is effective international cooperation, low consumption, and low population growth. At the other end is a fossil fuel development world with high consumption and high growth that will, of course, lead to higher warming. The range of these scenarios allow policymakers to look at different alternative futures if different decisions are made. The RCPs outline different potential trajectories for greenhouse gas emissions over time. They describe different levels of radiative forcing, or how Earth's energy balance will change, that might occur by the year 2100 due to increases in greenhouse gas emissions in the atmosphere. Like the SSPs, there are also 5 RCPs, and these are identified by the amount of radiative forcing projected by the year 2100 in watts per meter squared. The lowest amount of projected forcing is 2.6, and the highest is 8.5. Current global climate policies and commitments fall far short of the greenhouse gas reductions needed to follow the RCP 2.6 pathway. Therefore, it is unlikely the world will be able to follow that track unless carbon capture is used to drive negative emissions. One of the higher scenarios is more likely. The two sets of SSP and RCP scenarios are used together to understand not only what future warming levels might be, but the path the world might take over the next decades to reach those different states. By combining SSPs with RCPs, researchers can create a richer understanding of potential climate futures that account for both the physical science of climate change and the socioeconomic factors driving or hindering mitigation and adaptation actions. When using these scenarios, it is important to understand the uncertainties that characterize the data products created from them. These uncertainties arrive from several sources, including from the multiple different future emissions scenarios that are used, the limitations of the global climate models on which the projections are based, and the natural variability within the Earth's climate system. While the SSP and RCP scenarios model different futures, in reality, actual future emissions remain uncertain. Different development trajectories or disruptions could take the world on an unforeseen path in the future, which might not be captured by any of these scenarios. Therefore, the SSP-RCP scenarios should never be viewed as certain or final. The general circulation models on which the projections are based are also subject to uncertainties. These models aim to capture complex climate processes, but some of these processes are not yet fully understood by scientists. So there is uncertainty in how those processes will drive future climate conditions. These climate models also must rely on some simplifying assumptions since they cannot capture all of the fine-scale processes happening everywhere in the world. Lastly, there is simply natural variability within the climate system that cannot always be predicted. So the future climate projections are our best estimate as to what the future world might look like. To account for these uncertainties, scientists will often run multiple scenarios with multiple different circulation models to try to capture some of the model variability. These multiple runs can then be compared to see where the models agree or disagree. We might have more confidence in areas of the world where many models agree and less confidence in where the projections diverge from model to model. Additionally, the models can be combined or averaged together to create an ensemble of future forecasts. No matter what route is taken to understand the uncertainty in future climate projections, it is important to report or communicate this uncertainty with any analyses or data products that are produced from these data layers. There is one thing for which scientists are quite certain, and that is that the planet is warming at an accelerating rate, and actions must be taken now to slow that warming and put the world on a path for a better future.